Operations. Automatic or manual rebalancing. There is one important question with regard to rebalancing that we have glossed over. Does the rebalancing happen automatically or manually? There is a gradient between fully automatic rebalancing. The system decides automatically when to move partitions from one node to another, without any administrator interaction, and fully manual. The assignment of partitions to nodes is explicitly configured by an administrator and only changes when the administrator explicitly reconfigures it. For example, Couchbase, Ryak, and Voldemort generate a suggested partition assignment automatically, but require an administrator to commit it before it takes effect. Fully automated rebalancing can be convenient because there is less operational work to do for normal maintenance. However, it can be unpredictable. Rebalancing is an expensive operation because it requires rerouting requests and moving a large amount of data from one node to another. If it is not done carefully, this process can overload the network or the nodes and harm the performance of other requests while the rebalancing is in progress. Such automation can be dangerous in combination with automatic failure detection. For example, say one node is overloaded and is temporarily slow to respond to requests. The other nodes conclude that the overloaded node is dead and automatically rebalance the cluster to move load away from it. This puts additional load on the overloaded node, other nodes, and the network, making the situation worse and potentially causing a cascading failure. For that reason, it can be a good thing to have a human in the loop for rebalancing. It's slower than a fully automatic process, but it can help prevent operational surprises. Request routing. We have now partitioned our dataset across multiple nodes running on multiple machines, but there remains an open question. When a client wants to make a request, how does it know which node to connect to? As partitions are rebalanced, the assignment of partitions to nodes changes. Somebody needs to stay on top of those changes in order to answer the question: if I want to read or write the key foo, which IP address and port number do I need to connect to? This is an instance of a more general problem called service discovery, which isn't limited to just databases. Any piece of software that is accessible over a network has this problem, especially if it is aiming for high availability running in a redundant configuration on multiple machines. Many companies have written their own in-house service discovery tools, and many of these have been released as open source. On a high level, there are a few different approaches to this problem illustrated in Figure 6-7. Allow clients to contact any node, for example via a round-robin load balancer. If that node coincidentally owns the partition to which the request applies, it can handle the request directly. Otherwise, it forwards the request to the appropriate node, receives the reply, and passes the reply along to the client. Send all requests from clients to a routing tier first, which determines the node that should handle each request and forwards it accordingly. This routing tier does not itself handle any requests. It only acts as a partition-aware load balancer. Require that clients be aware of the partitioning and the assignment of partitions to nodes. In this case, a client can connect directly to the appropriate node without any intermediary. In all cases, the key problem is: how does the component making the routing decision, which may be one of the nodes, or the routing tier, or the client, learn about changes in the assignment of partitions to nodes? Figure 6-7. 3 different ways of routing a request to the right node. This is a challenging problem because it is important that all participants agree, otherwise requests would be sent to the wrong nodes and not handled correctly. There are protocols for achieving consensus in a distributed system, but they are hard to implement correctly. See Chapter 9. Many distributed data systems rely on a separate coordination service such as Zookeeper to keep track of this cluster metadata, as illustrated in Figure 6-8. Each node registers itself in Zookeeper, and Zookeeper maintains the authoritative mapping of partitions to nodes. Other actors, such as the routing tier or the partitioning-aware client, can subscribe to this information in Zookeeper. Whenever a partition changes ownership, or a node is added or removed, Zookeeper notifies the routing tier so that it can keep its routing information up to date. Figure 6-8. Using Zookeeper to keep track of assignment of partitions to nodes. For example, LinkedIn's Espresso uses Helix for cluster management, which in turn relies on Zookeeper, implementing a routing tier as shown in Figure 6-8. HBase, Solar Cloud, and Kafka also use Zookeeper to track partition assignment. MongoDB has a similar architecture, but it relies on its own config server implementation and Mongo's daemons as the routing tier. Cassandra and Ryak take a different approach. They use a gossip protocol among the nodes to disseminate any changes in cluster state. Requests can be sent to any node, and that node forwards them to the appropriate node for the requested partition. Approach 1 in Figure 6-7. This model puts more complexity in the database nodes, but avoids the dependency on an external coordination service such as Zookeeper. Couchbase does not rebalance automatically, which simplifies the design. Normally it is configured with a routing tier called Moxie, which learns about routing changes from the cluster nodes. When using a routing tier or when sending requests to a random node, clients still need to find the IP addresses to connect to. These are not as fast changing as the assignment of partitions to nodes, so it is often sufficient to use DNS for this purpose. Parallel query execution. So far we have focused on very simple queries that read or write a single key plus scatter/. Gather queries in the case of document partition, secondary indexes. This is about the level of access supported by most NoSQL distributed data stores. However, massively parallel processing MPP relational database products, often used for analytics, are much more sophisticated in the types of queries they support. A typical data warehouse query contains several join, filtering, grouping, and aggregation operations. The MPP query optimizer breaks this complex query into a number of execution stages and partitions, many of which can be executed in parallel on different nodes of the database cluster. Queries that involve scanning over large parts of the dataset particularly benefit from such parallel execution. Fast parallel execution of data warehouse queries is a specialized topic, and given the business importance of analytics, it receives a lot of commercial interest. We will discuss some techniques for parallel query execution in Chapter 10. For a more detailed overview of techniques used in parallel databases, please see the references. Summary. In this chapter we explore different ways of partitioning a large dataset into smaller subsets. Partitioning is necessary when you have so much data that storing and processing it on a single machine is no longer feasible. The goal of partitioning is to spread the data and query load evenly across multiple machines, avoiding hotspots nodes with disproportionately high load. This requires choosing a partitioning scheme that is appropriate to your data, and rebalancing the partitions when nodes are added to or removed from the cluster. We discussed two main approaches to partitioning: key range partitioning, where keys are sorted, and a partition owns all the keys from some minimum up to some maximum. Sorting has the advantage that efficient range queries are possible, but there is a risk of hotspots if the application often accesses keys that are close together in the sorted order. In this approach, partitions are typically rebalanced dynamically by splitting the range into two subranges when a partition gets too big. Hash partitioning, where a hash function is applied to each key, and a partition owns a range of hashes. This method destroys the ordering of keys, making range queries inefficient, but may distribute load more evenly. When partitioning by hash, it is common to create a fixed number of partitions in advance, to assign several partitions to each node, and to move entire partitions from one node to another when nodes are added or removed. Dynamic partitioning can also be used. Hybrid approaches are also possible, for example with a compound key, using one part of the key to identify the partition and another part for the sort order. We also discussed the interaction between partitioning and secondary indexes. A secondary index also needs to be partitioned, and there are two methods: document partitioned indexes, local indexes, where the secondary indexes are stored in the same partition as the primary key and value. This means that only a single partition needs to be updated on write, but a read of the secondary index requires a scatter/gather across all partitions. Term partitioned indexes, global indexes, where the secondary indexes are partitioned separately, using the indexed values. An entry in the secondary index may include records from all partitions of the primary key. When a document is written, several partitions of the secondary index need to be updated. However, a read can be served from a single partition. Finally, we discussed techniques for routing queries to the appropriate partition, which range from simple partition-aware load balancing to sophisticated parallel query execution engines. By design, every partition operates mostly independently. That's what allows a partition database to scale to multiple machines. However, operations that need to write to several partitions can be difficult to reason about. For example, what happens if the write to one partition succeeds, but another fails? We will address that question in the following chapters. The Apache HBase Reference Guide, Apache Software Foundation, hbase.apache.org, 2014. Eric Redmond, A Little Ryak Book, version 1.4.0, Basho Technologies, September 2013. Couchbase 2.5 Administrator Guide, Couchbase, Inc., 2014. Introduction to Cassandra Query Language, Data Stacks, Inc., 2014. Ryak 1.4.8 Docs, Basho Technologies, Inc., 2014. Apache Solr Reference Guide, Apache Software Foundation. 2014. Amazon DynamoDB Developer Guide, Amazon Web Services, Inc. 2014. Eric Evans, Rethinking Topology and Cassandra, at ApacheCon Europe, November 2012. Project Baltimore Documentation, projectbaltimore.com. Moxie 1.8 Manual, Couchbase, Inc. 2014.